recording as well. This is ODL lab number 2 and I hope everyone can hear me out. I'm going to share my screen as well. Again, I'm going to use the same method. Okay, so just please anyone confirm me out that the voice is being heard on the other side. And hopefully today I have the camera set up also as well. Actually this time which I take over here is just for this table and all this stuff. So I have to actually be very careful. So this all is working and this is actually, let me just change the okay, so this is the very same. I hope everyone can see this. Okay, so I hope everyone has gone through this experiment circuit diagram. This is actually a very basic circuit diagram. I hope everyone can see this circuit diagram. It's available on the web link also and I have also shared this one over here. If you remember last time we had a common anode and I told you what was a common anode. Common anode meant it was actually something like this. If I can show you, it was something like this. If I can hold it over here, it was just like simply the very same thing. Here the center pin over here on this side, this was the common anode point from where the current was actually going to enter, and it was actually going to come out from this F, G, A, B, C, D and whatever stuff over here. Now this time, as you can see, the shape is exactly the very same, nothing different over there. The only thing different is this, that this time it's not common anode, it's common cathode, and common cathode means that instead of providing from that common central point over here, this is grounded, which means you are actually going to provide a sinking ground or sinking path over there. And I hope you remember I told you that a sinking meant over here that the current was actually going to sink towards the ground. Now you can see over here, this time instead of providing this A, B, C, D, E, F, G, this time I am using an IC. And this IC is going to be used over here today as well. And as you can see over here, it's also placed over here. This second IC over here is not usable. I'm not going to use it today. I just placed it over there. Most probably in the next lab I will make this whole as a jumble over there. Now as you can see over here, I have done the circuit diagram already over here, and I will explain this one just in a bit over here. But before that, if I go towards the again the circuit diagram over here, you can see what is this IC doing. This IC is taking, I will give you the data sheet also over there just now. This IC is taking A, B, C, D inputs, or you can call them as D0, D1, D2 and D3. Take them as the very same. A is the least significant bit. Now what this means over here, that I am actually talking about a 4-bit binary number. You are all familiar with binary numbers up till now. Binary number means that it either can be 1 or 0. And here 1 is actually going to be meaning that I am going to provide 5 volts. And binary 0 means I am going to provide a ground. So as you can see over here on this A, B, C and D, you are actually having A provided through a push button, and that push button we have talked about previously. This push button is available over here as by this dip switch over there. I hope everyone can see this video and all that. It's being recorded, so I hope even if there is some lag you can have a view afterwards. So this A, B, C and D are actually D0, D1, D2 and D3. So just like you have always a binary number with D0 as the least significant bit, D1 as the next bit, D2 as the next one, D3 as the next one, and this is being provided through push buttons. And as you will press any one of them or maybe all 4 of them, supposedly you are pressing all 4 of them, you are providing actually 5, 5, 5, 5 on all these 4 pins. So this is 5 volts here, 5 volts here, 5 volts here, 5 volts here, and this is actually 1111 binary. And if you transfer this one into decimal, this is actually called as 15. if you remember it. You can convert a binary conversion into your decimal. This is actually 15. But the point over here is it that you are only having a single digit over here. So a single digit means that you can only display a number from 0 to 9. So when you want to display a number from 0 to 9, this means that the maximum value which you can actually give from this push button is actually on pin number D, or you can call it D3. In the circuit, next circuit diagram I will show you that one also. This is actually changed to D3. So D is giving, you press this push button, you press A. So you are providing 5 volts here, you are providing 5 volts here, these two are not on. So this means through this 1 kilo ohm resistance you are providing 0. So these 1 kilo ohm resistances are being added over here so that you can actually have 0 provided if these push buttons are not working. So these push buttons are not working, you are providing 0, 0, 0. So if any of the push button is not pressed, you will have a 0 displayed over there. So what this IC is doing, it has its 0 to 9 code embedded inside it. These are some control pins. I will talk about this control pins just later in a data sheet. So what I am doing over here, if I provide 0, 0, 0, 0, there is going to be provided from QA, B, C, D, E, F, 5 volts. All that 5 volts which is being provided to this IC, it is going to be provided through this 7 pins. G is not going to be provided. Why? Because G is this central segment over there. So A, B, C, D, E, F, they are all going to be lighted up. So you are going to have 0 displayed over there. Now I will show you this one just now as well in on a live as well. But I have these over here. Let me just show you. I have this all digits. I have already done this before over here. And you can see what I have done. Now I hope everyone can have a look on this one. What is this? If you can see on this one, I will give you the live presentation also on this one. You can see the same structure has been done. I'm showing you over here this IC. This is 4511 over here. These are what are the bits and how it's connected. You can see 1, 2, 3, 4, 5, 6, 7 resistances of 330 ohms connected. Now you can see I have taken these jumper wires from here to here. And at this present time, none of the dip switch is on. So you can see you are providing 0, 0, 0, 0. So this means you are going to have 0 displayed over there. And in the next diagram, you can see what I have done over here. This is D0. The fourth dip switch in this picture is D0. This is D1. This is D2 or D3. Or this is A, B, C and D. Or in other words, the same diagram. So this is called as 0, 0, 0, 1. So 1 is the least significant bit. You convert that one into decimal. This is 1 displayed. And if I continue this on, now if you see this one over here, what is this? This is 0, 0, 1, 0. So I have kept the least significant bit on this side of the picture. So this is 0, 0, 1, 0. So this is 2. And in the next picture, as you can see what I have done 0, 1, 0, 0. Now this is 4. Why? Because this is, if you remember your binary strengths table, this bit was having strength 1, this bit, second bit was having strength 2, the next one was having 4, and the next one was having 8. So when I will do this one, you can see I have in number, we have taken this 1, 0, 0, 0, so now 8 is being displayed. I have done all the other segments as well. You can see this is 9 displayed over there, and then this is 3 because this is 0, 0, 1, 1, and then you have 0, 1, 1, 1 because this is 8 is off, so this is 7, and then I have this as 6 because 4 and 2 is on, so 6 is on, and then I have this as 5 because this is 4 and 1 is on. So I have all the digits over here, so this is working. Now coming back to what I need to actually do over here, I need to have the 74HC4511 data sheet. Now please, this is your first time you are going to see a data sheet now. So first of all, always try to take a data sheet from some notable manufacturer. Now as time will pass on and you will have an understanding that these data sheets, the most notable manufacturers are Texas Instruments, Fairchild, Analog Devices and all many others over there. So these 3 or 4 names which I have taken just now, you can use these names as the, so whenever you are going to do a Google search or something like that, please always go for some Texas Instrument. This is ti.com, so this is Texas Instruments website. So I hope this is actually opening at present. Let me just check on. Okay, so this Texas Instruments website, this is opening at present. So I will just, so data sheet is open. Now I hope everyone can have a look on this one. I can just turn this off and I hope everyone can have a look. I have opened it from a Google link so everyone can open it on your end yourself also. This is being recorded as well, so no issues if you don't even open it afterwards. You can see over here, as you can see, the first thing first, you have to tally the name matches. That is 74. 74 is actually a series in which all the logic gates, now you have done work on your logic gates in your FSC. So you have already an idea that how you are going to handle logic gates. So if you are want to finding out a logic gate, NOT gate, OR gate, AND gate, you can find it. So 74 is actually the series number. HC is actually the speed over there. I'm not going to talk more on that one. In next classes you will talk about a little bit in more quantity. Over here, what you are seeing over here in this pin configuration, you can see this is a DIP package. How? This I will go on the lower portion of that sheet afterwards. If you see, there is a notch, and that notch, if you place your IC, now if you can, I can zoom it a little bit or more over here. So if you can see over here on this one, you can see either there is a notch or either there is a dot over there. Now this notch is not there. You can see on this IC there is a notch. On this IC there is not a notch. Even in fact, if you can zoom a little bit more, you can see a little slight notch, but over here they have put a small dot mark. It's actually an embossed thing over there. So this means this is facing towards you. I have placed this on a breadboard. This is pin number 1 where my mouse with my ballpoint is at present. 1, 2, 3, 4, 5, 6, 7, 8, and then you will go on the top. This is 9, 10, and you get it down to this is 16. So this is the very same. So whenever you are having a DIP IC and you want to actually find out that what is your pin starting number 1, place this IC name towards you. The notch should be on the, or the dot point should be on the left side and facing towards you, starting from the extreme left. You're starting on over there. This is pin number 1, to pin number 8 over here, and then pin number 9, and then pin number 16. So from here to here like this, this is pin number 1 to 16. Now if I go back on your data sheet over here, you can see over here, I will just zoom, just rotate it a little bit so everyone can have a look what I actually wanted to show you. You can see this is pin number 1, so this is D1, pin number 2 is D2, pin number 7 is D0, pin number 6 is D3, pin number 8 is ground, and then on the topmost I have VCC where you are actually going to provide 5 volts. And then there is F, G, A, B, C, D, E. So these are the 7 segment outputs which you are going to actually attach them to your 7 segment, that is common cathode over there. So you can see over here pin number 1, 2, 6 and 7, they are BCD inputs. What does BCD stands for? BCD stands for binary coded decimal. Now as the name speaks for itself, binary coded decimal. What does binary coded decimal means? This is a decimal, this is coded into binary. So you are giving a binary signal at D0, which is the least significant bit, D1 the next one, D2 the very next, D3 the very next. So you are providing a 4-bit number, you are providing VCC and ground to the IC, that is 5 volts and ground certainly, and then you are going to have F, G, A, B, C, D, E, just like you have done previously. In the experiment you had a 7 segments, so you just have to connect through this F through a resistor, just like I have done over here on this breadboard at present. Now I am not going to show you that over here how this is being connected. The video is, G beta, please. Beta, my voice should be clear, I guess. I think so. I guess this is on your side, please. Acha, one thing very important throughout this now, only CRs can actually open their mics, please, no one else. And one more thing, I just saw in the very start, roll number 55, I thrashed him out of this meeting. If I see him again doing what he was doing previously, you will be penalized by 1 grade in this lab. So please do not open your mic when I am speaking. I have muted everyone, but if you will create a chaos for me during this class, I will penalize you. Only CRs are allowed to open their mics. If you want to say something, then you can do it. Otherwise, just write down in the conversation window. Okay? Any questions up till now? Please write down in the conversation window about this IC or the 7 circuit diagram or this experiment circuit diagram. Anyone, anything. Please write down in the conversation window. So I hope everything is clear from this side. And anyway, coming on to again the data sheet. So you can see over here, you have this IC, just like the very same you have over here on my camera. And you can see this one, I have this running. And I will just show you the running procedure as well just now. I will on the supply, I will give 5 volts and I will show you. Otherwise for you all, I have shared the digits also in running condition. I have taken some pictures and I am going to share these pictures also. I have asked Sir Bilal to share them on his website. They are also available on my website. Plus there is a whole collage also which is shared by me as well on the website as well, my website as well. So you can see this is 01234567889 over there. Coming back to the data sheet because I want to cover that and then we can go on forward. Data sheet over here, as you can see, some more things which you should be reading on at least as first year students still. If you read down these points, bullet points over here, what are written over there? 2 volts to 6 volts VCC operation. What this means, you cannot apply more than 6 volts to this IC. Okay? Now 7 segments which you are using, they can only turn on when you are going to provide something of more than 2 volts. So this means that you are going to provide some 5 volt. So they are going to have a resistance of 330 ohms used over there. So certainly this means that your operation is actually going to be just for 5 volt, not 6 volt. And since I am going to just have the 5 volt IC over here, so 5 volt is the 7 segment. So I'm going to use that one. And if you are using 74HC4511, which is actually our case as well, because I have 4 HCT, if I can show you as well on this one. And actually this is HC, not HCT. Anyway, so I can use it for 6 volts also. Next thing, high output sourcing capability. This statement actually tells you that the outputs F, G, A, B, C, D, E, they can actually source a current of 7.5 milliamperes at 4.5 volts and they can output 10 milliamperes at 6 volt from HC4511. Since I am using over here, I can source approximately 10 milliampere at 6 volt. So I am using this one at 5 volt. So this means certainly that I will be something near about 8 or 9 milliampere. But I am not going into that physics and that calculations over there. Then the next statement, input latches for BCD code storage, which means that inside this IC they have made all those storage points. They have done the table inside it, the truth table, just like you, if you remember your FSC, you had those truth tables for AND gates, OR gates, NAND gates, or whatever. Just like over here, you have some tables over there, and those are stored over there inside this IC. I will just show you that table as well. Just scroll down a little, I will have that view as well. Lamp test and blanking capability. Now you can get the idea. What does LT mean over here? This third pin, LT, that means lamp test. So sometimes when you are actually doing some debugging and you want to actually test it, that your IC can test it out, and the blanking capability. BL stands for over here blanking capability. So you can actually blank whatever you are displaying over there. So from the controller or from any Arduino, I don't know how many of you are capable of or have heard about Arduino or any other microcontroller up till now or microprocessor. So you can give any signal from any third party controller or whatever, so that you can give a lamp test and blanking capability, and you can turn off or you can test your IC. Then next thing, balanced propagation delays and transition times, which means that all the segments F, G, A, B, C, D, E, all of them, they have a balanced propagation delay. It's not like this. If you are giving a continuous signal, so all of them is going to have a continuous equal propagation delay time over there. And then the next thing is the significant power reduction compared to. Now this is a logic IC Previously, now since these ICs have actually come from the last 40-50 years of enhancements in technology, so there is a significant power reduction over there. The previous logic that was LSTTL, I am not going to talk about more on this one, and your further classes you will understand that this what does LSTTL mean over there. Now coming on to the next 2 points over there, they are just the input logic, some values over there. Now if you want to order this IC, supposingly you want to online, then there is an ordering information. You can see the packaging. Here it is written PDIP. PDIP mean package in dual inline package over there. PDIP stands for very same which I am using over here on this breadboard over here. So this is the very same IC which I am using over here, that is PDIP. If you want to use a SMD, surface mount, then you can use SOIC or TSSOP. We will talk about them in later on when we are going to move from DIP packages to the SMD packages over there. But up till now I am using PDIP package and it comes in a tube of 25. But this means that you are going to have packaged of 25 DIP ICs packaged together. So they are actually going to come in a tube. Maybe in some time I will show you a tube as well in practically over there. Now the thing actually I want to show you is this table, just like a truth table of AND gate or gate. What you have to do, these are inputs. You can see D0, D1, D2, D3. They are arranged in bits over here. So D0, D1, D2, D3, they are arranged in least significant bit, the next one, the next one, the next one, and then these three are inputs. Now you can see what we have done. Lamp test and blanking, they have been given high. So this means I am not even testing. I am not even having, so you can see there is a bar on it. LT has a bar on it. What this means that whatever logic you are going to give it, it's going to actually convert it into its NOT. So there is a NOT gate included over there. So this means I am giving LT, lamp test and blanking over here as high. So when it's going to be converted into NOT, it's going to be actually converted into low, so it's going to take the signal inside over there. Then there is a LE input, and I hope LE is being given low over here, so it has an internal schematic. So you can see these three signals are hard coded, which means you are not going to change them through over here. And if I show you on this one, now what is the data sheet telling us that BL and LT, they have to be given high and LE has to be given low. High means 5 volt, LE means 0. So if you can see on this one, over here I have this third pin connected to VCC. You can see this jumper wire. So from this third pin I have connected this with VCC, and from this VCC you can see this green color wire connected to 5 volts over there. There are some jumper wires over here, don't confuse them with the other ones over there. Other one are this one. So I have this third one, and then I have the fourth one and the fifth one. You can see this is connected. Actually you can't see much a lot. I have more jumper wires over here, but I have connected the fourth and the fifth pin to ground over here. And you can see the ground connection is done through this green color again wire. As you have seen the circuit diagram, I will again go on the circuit diagram. You can see you have your LT and BI, third and fourth pin connected to 5 volt and fifth pin connected to ground over here on this circuit diagram. Let me just check if there is any okay, I guess Bilal is actually taking care. Okay Bilal, thank you. You can take care on the question and answers on the camera or whatever. Oh, the conversation. So over here, these three are just fixed inputs, just like over here. So third and fourth, you can't actually see the jumper wire. I have placed a jumper wire just below this one. So third and fourth, I have combined them together over here, and then through a jumper wire, I have taken them to VCC, and from the same hole, I have taken it to VCC. So third, fourth pin have been given 5 volts, and the fifth pin you can see from here to here where mouse is hovering. This is the ground connection, and from here the ground connection is done over there. The whole breadboard, the topmost line is VCC, here it is ground, and you can see this jumper wire. So this is VCC connected to here because this dip switch is being provided 5 volts from here. So you can see the old schematic over here. Now the next thing, if I go on the circuit the data sheet again, sorry. Inputs D0, D1, D2, D3. Just like the circuit diagram I have shared with you, you are either going to give them low, high, low, high. You can see this is 0, 0, 0, 0. So what will happen? A, B, C, D, E, F will be high, G will be low. This means that G is not going to be lighted up because from the second circuit diagram, from the 8th, this is current is flowing through this resistance and then it's not going to be lighted up. So if you are displaying 0, you are going to have only 0 displayed over there, and the current is actually going to travel towards the ground path over there. So this truth table, as you can see, or a function table, as you can see, you can display from 0, 0, 0, you can see you can display a 0, or you want to display a 9. Now if you give more than 9, because that is also possible, this will be blank. Why blank? Because there is only one digit practically over there, so it can't display 2 digits, it can't display 1 and 0. So that's why they have embedded over there. If you give 1, 0, 1, 1, it's going to be blank. Even if you give 1, 1, 1, 1, it's going to be blank. So this means that you can only display from 0 to 9 over there in this condition. And if you want to go towards the logic diagram of this IC, this is that functional diagram, and I hope so those who are a fan of AND gates or NOT gates, they can have an understanding that how this is working. You can see the A, how it is being formed, B, how it is being formed. You can see a lot of NOT gates. You can see a NAND gate, a 3-input NAND gate. You can see again a NOT gate over there, or a buffer over there. So you can see all this. Whatever it is, it's a NOT AND gate common thing, and it is being coded inside all this IC which we are using here today, which is having a 5 volts over here, ground over here. So by having this 5 volts and ground, you are actually running this IC, you are giving 5 volt signal to this IC, and when you are going to give dip switches. Now one thing only over here, if you see the circuit diagram back over there, since if I don't connect this 1 kilo ohm resistances, these are going to be open, which means A, B, C, D, they are going to be not getting 0 volts. So I want them to getting a 0 volt. So through this resistance, I am providing them 0 volts. So the push button, when it is not on, I am providing 0 volts through this 1 kilo ohm resistance to each A, B, C and D. And again, I am taking this confusion away. A, B, C, D are the very same things as D0, D1 and D3 in this function table. So this is A, B, C, D. Okay? So don't confuse yourself, because in some data sheets, if you take on from any other manufacturer, maybe you will find out A, you will find out B, C, D, or in someone you will find out D0, D1, D2, D3. The word D is used, or letter alphabet is used over here because this is digital. So this is D0, D1, D2, D3, and I hope already you have an idea what is A, B, C, D, E, F, G. Now let's come on to how this is going to function. I will just show you the meanwhile, any questions, if anyone, I guess hope so Bilal has answered on this one. Okay, I hope so Bilal is actually answering them. I will just connect my power supply with this 5 volts and all this, and I hope everyone can have a look on this one. So this is my 5 volts I'm connecting. Let me just zoom out a little. Okay. Okay, I hope everyone can have a look. So you can see already, because some switches were on. So I hope everyone can have a look. Let me just zoom it a little bit more. So okay, so I hope everyone can have a look. Why 5 is displayed over here? Because I have 1 over here, because I have connected it with 5 volts over here. And here I have done, again, this is 1, this is 2, this is 4, so 4 and 1, I have displayed 5 over there. Now I want to display supposedly 9 over there. So what I will do, I will turn this off. You can see now only 1 is displayed, and now this is 9 displayed over there. Now just to verify that functional table, if I give a signal of maybe 9 plus 2, it should display 11, but I have told you that the IC is not capable of it, because there is only 1 digit over there. So this means I can only display a single digit, that is from 0 to 9, and you can see the whole circuit diagram over here. Very simple, the circuit diagram is there, and I have shown you on the breadboard. I am going to share this picture as well. You can display anything, I guess. Let me just show you maybe 3 displayed over there. So this is 3 over here, and if you want to have a like 7, so this is 7 over there. So you can do anything that is required. And now one thing very important. Now this is dip switch. You don't want every time a dip switch, because you want this data to be given from a microcontroller. So when you are going to use a microcontroller, your microcontroller is actually going to give this signal not from this dip switch. You are actually going to place a male header, and that male header is actually going to be placed here, and this data is going to be given through some 4 digital pair of wires coming from some microcontroller. So this 4-bit data which is being provided by this dip switch, it is going to be provided by 4 digital wires coming from maybe a computer, maybe a microprocessor or a microcontroller. So you can display anything on the 7 segment over there. Now coming on to the main circuit diagram, which is actually our circuit diagram for this lab also. I hope sorry, not this one actually, let me yes, this is the circuit diagram. I hope everyone can have a look at this one. This one is the same thing, the only 2 things which are added over here. What are those? If I just zoom in over there on this one, you have 74HC4511, you have D0, D1, D2 and D3, and they have 1 kilo ohm resistance. You have again the dip switch. But when you are going to make the PCB, okay, this is very important, when you are going to make the PCB of it, you are actually going to connect a male header. What is a male header? A 4-pin male header with a dip spacing of 2.54 mm, that is standard. So you are going to have this connected on D0, D1, D2 and D3, certainly in some order, D0, D1, D2, D3. I have made D0 since this is the least significant bit, so I have taken it on this side, on the right hand side, D1, D2 and D3. And then I have this over here as D0, D1, D3. So this is going to give the data. From this F, G, A, B, C, D, E, this is going to be connected to this common cathode 7 segment over there. So this is the common word used over there, and I can have common cathode connected over here in this way. And then over here are 2 differences over there. I have connected an Npn transistor. As you can see, I hope everyone has an idea what is an Npn transistor. Now I'm not going to go in the physics of an Npn transistor. You already know that an Npn transistor has this symbol which I have drawn over here, and over here I have connected a 1 kilo ohm resistance with this transistor. So when I'm going to give a 5 volt signal on this, it's going to be forward biased. This is the base, as you can see over there. I can just zoom in a little bit more. This is the base, this is a meter. So what I am going to give a 5 volt signal over here, this is going to conduct electricity or current from the B to E. It's again a conventional current flowing. So what will happen? The current can flow now from the collector to the emitter because the transistor has been made forward biased. So what is going to happen? Your circuit has already provided that current from G, F, A, B, E, D and C from this IC. So that same current is going to travel through this common pin through a resistance. Now this resistance, why I have added it? Now this resistance can be any value from 10 ohms to 33 ohms, but I have added 33 ohms just in case, so I don't have a larger current flowing through it. This transistor name which I am using over here is 2N3904. I will show you the data sheet as well just now. So when you are going to have 2N3904 data sheet, you are going to have only 100 milliamperes of current. Now 100 milliampere of current, I hope so if even every segment takes on approximately even 10 milliamperes of current, just like you saw in the data sheet. So even you are just going to have like 70 or 80 milliamperes of current. So that's enough. So 70 milliamperes of current, when it is passing through this resistance, you can have this resistance at just 10 ohms, 22 ohms, something 33 ohms. It's totally up to you. So this is just going to allow. Now what this transistor is actually achieving me over here. Previously, what we wanted to do, I wanted to connect this common wire with the ground. So this IC, when it was providing that A, B, C, D, E, F, G signals, so the common was going to get ground and the signal was being displayed. Now, sometimes I want this segment to be off despite whatever signal is being given from the IC. So I am using a 2-bit dip switch again over here, and again I have a male header connected over there, so that when I will on the switch, then this segment is going to be on, Otherwise, this segment is not going to be on. This is very important. I hope you get the idea. I can connect this common wire to ground just like I have shown you over here, just like this one. This is the common wire connected to ground. But I have done over here in this way that through this common, it is passing through an Npn transistor 2N3904. It's an Npn transistor, and I hope everyone has an idea from your FSC that Npn transistor, it turns on when you give the base emitter junction a forward bias. So you are giving a 5 volt signal at, please turn off your mics please. So you are giving a 5 volt signal at this one, again a resistance over there, you can call this one as the base resistance, and then there is an emitter over there. So this emitter is going to be forward biased, and then because of this being forward biased, current can now travel. Now if you don't give a 5 volt signal over there, what this means, that the transistor will not turn on. So you have actually effectively made a simple switch. So this switch is being controlled from a dip switch or maybe a male header. This can provide a signal from your microcontroller or something, but a switch is now there so that you can now control either you want your display to be on or off digitally. Any questions from this, please ask me in the conversation window. Gee, any questions? Please turn off your mics. 71, please turn off your mic. There is a lot amount of static noise from your I'm just okay, I will just repeat the process of switching, don't worry. I'm going to repeat it again. Okay, now what is happening? Your IC 74HC4511, you are providing that D0, D1, D2, D3 signals over here, and you are having all these signals provided to the IC. You have supposedly given 0, 0, 0, 0. You wanted 0 to be displayed. So you are having, apart from G, you are having F, A, B, C, D, E, all are providing signals and they are going towards. I have not shown the connection from this F, G, A, B, C, D. They all are connected over there because that would create the whole diagram. So that's why I have given them the names over here, F, G, A, B. You can connect them yourself because you are going to do this on the software. So when you've done it, now you want that common point so that it's going to take all the current and sink the current to ground. What I have done over here, I have added a small transistor, and that transistor is an Npn transistor, and I am now making it, working it as a switch. Now this switch can be controlled digitally. How? I am going to provide 5 volt signal at this base pin through a 1 kilo ohm resistance. Okay? And don't go into the calculation physics, why this is a 1 kilo ohm resistance, why this is a 33 ohm resistance. You have ample amount of time. In your next 4 years, you will get a lot amount of all these calculations. So I'm not going in that calculation. Even if anyone is interested, I can make a small video for you and I can give you the calculations also. But just for now, I'm only interested in controlling this switch. Now, how this is working as a switch, when I will give 5 volts over there, base current will flow from the base towards the emitter, making the base emitter junction forward biased. So when this will become forward biased, the collector to emitter, which is actually the main current flowing, which is actually the collector current or the emitter current. So from this common pin through this resistance, what will resistance do? Again minimize that current. Even if you don't use that resistance, the circuit will still work. But chances are this, that supposingly this resistance fails. Okay, you have not connected the resistance, or maybe the resistance goes to 0. So what will happen? You will have a very huge current flowing through this transistor. The 7 segment will also burn and the transistor will also burn. So I have taken a very small resistance. You can make this value to 10 ohms, 22 ohms or something, 33 ohms. I have added over here so that it is scanned. So 33 ohm resistance, not that big. That one which I have used over here, this is a 330 ohms. So 330 ohms mean that I am actually just using 10% of that value over here. So now when this current is going to be reduced, this is going to go towards the ground. Now the next thing, if I off this switch, even whatever the signal is being provided from the IC, the dip switch is not on, or you are not providing a signal towards your male header. This is the male header pin. So the switch is not turned on. So when the switch is not turned on, you are not letting the display turn on. So this means you have added a switch in the common point from here to ground. I have added a switch. So this transistor is actually working as a switch over here. It's an Npn transistor. So what happens, even if your IC is providing current, if the switch is not turned on, you are not going to have. So sometimes you want to display the data, but you want to turn it off instantly. So this can be done over here. You don't need to change the data from there. You just need to make the switch off and the display will be off. Now, apart from this, G, please turn off your mics. Please turn off your mics. Just let me. Okay, coming on to the next transistor. Now, what I have done, I have used another transistor over there. Now, what that transistor is doing over here? Now, you know, there is also a data point. Now, that data point is not being controlled by this IC. There is no IC which is having a data point also. So, sometimes we want to display the point also. So, what I have done over here, I am using again a switch transistor which is going to turn on this DP through that transistor, and this time I am sourcing the current to DP. This is very important over here. This transistor, since this is connected to VCC, there is a 470 ohm resistance. Now, why I have used a 470? Why I have not used a 330 ohm? The answer is very simple, because you can see the segment, the physical segment of here, this one as compared to this dot is very, very small. So the dot is having a very small current. So that's why I have used a smaller current to flow through it. So I have used a little larger resistance. So again a 1 kilo ohm resistance on the base. Again this is connected to the second pin of that 2-bit switch. Again a male header so that I can provide this signal from a microcontroller. So if I want to press, I will turn this on, or maybe provide from a microcontroller on this male header. And then I will turn on this transistor just by the same logic. Current is going to flow from this 5 volt through this resistance and through this transistor to the DP pin, and from the DP pin, if the common resistor is having the current flow through this transistor, it will be turned on. So if you want to have a DP on, not only this should be turned on, the lower one should be turned on, because this is taking the all current from all the segments. Why? Because this is a common cathode display where all the currents, they actually go towards a common point. That's why it is called the common cathode display. So I hope everyone has an idea why these two transistors are being used over there. I have written some statements over here in this one. So I just read it about the upper transistor. This one is used for controlling DP, data point, of the 7 segment on or off. 2-bit dip switch, just like over here, the blue color one, the 2-1 over here is used, one for DP, the other for controlling the 7 segment. So this one you can take it as the master. This one is just controlling the DP, but it will not just control the DP unless and until this is turned on. So this is actually the main transistor. So you want to turn off the whole display, even the IC is getting some data or not. So I will just turn off this dip switch and everything will be off. Then I have the lower transistor is used for controlling 7 segment on and off, just like I said just now. Male headers are used for connections to microcontroller. So you are going to have this male headers over here at this point and this point. You can in fact use this one and this one as the very same. No need of having 2 pins over here for this one. You can just use only 1 2 pin and connect them with these 2 over here, and that can be sufficient over there. No need of having 2 separate pins for that, 2 separate. That will actually just clog the place. So all A, B, C, D, E, F, G pins are directly connected to their respective pins at 74HC4511 through resistor, and that resistance is 330 ohms. And then I have male headers for digits D0, D1, D2, D3, and two transistors are must for connection with the microcontroller. Now you want to control all of this circuitry which is on this region, and you want to control this one through a microcontroller. You want to give a signal, maybe you want to display, at one time you want to display 0, maybe supposing this is a counter at some bank, and you want to actually display, so maybe when one person has gone, the sensor can give an output, okay, you are now going to increase from 0 to 1, okay, then 2, then 3, then 4, then 5. It's not just going to be based on something, it's going to be controlled from some microcontroller, some microprocessor, some computer. So I will show you in fact also. I will select in fact this week's assignment when I am going to, whoever submits me the assignment first, I will make that person's PCB over here in my lab, and it should be small, certainly it should be small, and whoever will make it first, I will hopefully on weekend, I will take that PCB design from the link submission and I will make that PCB, and hopefully in the next class I will show you the control from the microcontroller, and I will show you that how 0, 1, 2, 3 and all that can be displayed over there. Okay. Now apart from that, before I move on towards the PCB part and show you, this time I am going to have the supply section also added. Now what is this supply section? I will come to the transistor data sheet just now. Just I am going to talk about this supply section. Just like I told you, there is going to be an input and this is going to be a regulator. Now what is this regulator? This regulator, as the name suggests, this is a regulation device which is going to take some input. Here this is 7 to 10 volts. It's going to take it on pin number 1. Pin number 2 is grounded. Pin number 3 is going to give out. Now this is 7805. 05 suggests that this is going to give out me a 5 volt output, and there is a capacitor added, and I hope I don't need to tell you that a capacitor is actually used to stable the output. So capacitor doesn't allow the voltage to change fastly. So this capacitor is being added. It's a polar capacitor. Again, what is a polar capacitor? Which has plus and negative sign included on the name of it. I will just show you physically also just now. And then there is a 330 ohm resistance and an LED, just like I showed you previously in the video. Also today I have not done on the breadboard because I knew it was working so already. So you are just going to add all of this power supply on the PCB also, which means you are going to use this LM7805. Now coming to LM7805, this is a regulator. Now if I go on my, let me just go on again Google, and now I want to talk about actually I have two PCs working over here and I was using the other series. This is 7805 data sheet. Okay, now I can go on the data sheet as well. In fact, I will select some good. Yes, this is LM Spark 1. So in fact, actually my upper bar is not visible. So okay, now you can see what is this data sheet telling you. This is micro A 7800 series. This is telling you that you can have a series at its positive voltage regulator. Now, which one is yours over here? I am using, let me just zoom it a little bit. It's a 3 terminal. The output current can be 1.5 amperes. As you can see over here, 1, 2 and 3. This one is the picture over here or this picture one. Either you are using any of these two. You can see there is a slight difference from this picture and this picture. The one which I am using is actually the lower one. So you can see if I just turn this one, let me just show you in straight direction. Actually, okay, sorry. Okay, I have this one. So I have this one. This is the common. This is input, common and output. And if you can see and read out this one, this is TO220 packaging. TO220 packaging. Okay? How this is named and all this nomenclature is how I will just talk about in the PCB design over there. You can see this is the input, this is the common, which means it's actually the ground part, and this is the output. So when I'm going to use this IC, how I'm going to get the output. Now one thing very important, if anyone is interested in the circuit diagram of this one, it's inside, but I'm not interested in that one because I just want to use this IC to get out 5 volts from my pin. Now when you are going to use this IC, I want to just show you how the input voltage is going to change over there. I want to actually talk about the 5 volt version. So if you can see over here, Recommended operating conditions, input voltage. Now, as I told you, it's a series. It has 5 volts, it has 8 volts, it has 10 volts, it has 12 volts, it has 15 volts, it has 24. So there are a lot of 6 different vans. 7805, which is our requirement at present, it has a minimum voltage of 7. So you have to provide 7 volt so that it can give you 5 volts constant output. And then there is a maximum input of 25. Now 25 I guess is a little bit harsh on this one. I don't normally apply more than 15 on this one, because more than 15 means that you are actually going to heat it up more. Okay? And maybe in the next class I will just tell you how a heat sink is going to be added. At present, this regulator which you are using, it's not going to be provided a regulator with a heat sink. It is just going to be the IC, that is 7805, which is TO-T220 packaging over here. As you can see, if you want to order this information, I am using TO220 over here. Again, it's available in a tube of 50. The orderable part number is micro A 7805 CKC, and output voltage is 5 volts over there. It's a simple regulator. It's the most common thing. Every time whenever you are going to try to use a power supply or something, and you are going to make a project in any of the course to maybe carry on in your final year or first year or second year, whatever, you are always going to require regulators. So whenever you require 5 volts, I will tell you also 3.3 volts also, because now all your laptops, your mobiles, your computers, everything, they are not working on now 5 volts, they are working at 3.3. And now even I guess those who are iPhone fans, they must have an idea that they are reducing their power consumption, and their battery is now a lot improved from their previous series. The reason is this, that now they are not working at 3.3 volts, they are now working at 1.2 volts or 1.8 volts. What does this mean by that? A binary 1 is actually taken as 1.8 volts, and binary 0 is taken as something as 0.0 or 0.1 or 0.2. So this difference is actually decreasing, so you have less voltage, you have less current flowing over there. But to develop a system in which you can have a binary 1 detected as 1.8 volts or 1.2 volts, something like that, it's actually difficult. So now the space race and all this stuff, the power consumption is a very important thing. Now since we are just first year students, so I am giving you this positive voltage regulators. They are not as good as any those devices which are being used nowadays, but as a newbie and as a fresh start in this course and in this electrical engineering department, this is the very first regulator IC that you can use very easily. It can output a current of 1.5 amperes. Though I don't know the ones you are going to get from Hall Road physically when you are going to make this all PCBs and all that stuff. Maybe it can't even handle 1 ampere, because there again you can call it Chinese and counterfeits or copies, because the actual IC price is more than like 100 or 150 rupees. But the ones which you get from Hall Road, they are just like 15 or 12 rupees. So certainly this means that they are counterfeit, but still they can handle 100 or 200 milliamperes of current, and that is enough for your needs on your PCB or on your Vero board or on your motherboard or whatever on which you are actually using those regulator ICs. Now coming on to the next thing, which is the transistor. Now again I am going to write that number. Now this is very important over here. I have 2N3904 datasheet. Now I will show that transistor also, and this one a little later just now. So I have this 2N3904. It's a very common transistor. The common price of this transistor is not more than 2 rupees, but as you can see, certainly it should be a 3-pin device. It should be a 3-pin device because it's at the base, emitter and collector. So as you can see, it has a marking on it, 2N3904. The packaging is TO92 packaging. TO92 packaging. It's a name given to it. The previous 7805 segment I just used, it was TO220 packaging. This one is TO92 packaging, and you can see on this diagram, the one I have shared just now, you can see on this one, this is TO92. Now you are not having that MO pack or TO90T. It's almost the same thing. The bulk and the MO pack, they are almost the same thing. Only thing is that the legs are actually bended. Otherwise, when you are going to buy TO92 packaging in the bulk over there, then certainly you are going to use having 1, 2, 3 1, 2, 3. What are 1, 2, 3? If I just scroll down a little, 1, 2, 3 are actually telling me that which one is base, which one is emitter, which one is collector. Now before I go on how you are actually going to tell by seeing the transistor in your hand, if I just go a little bit down, I have some ratings over there. Now I hope everyone has an idea from your FSC that there is a transistor rating over there for every transistor. This transistor has a rating of 60 volts. This means that you can apply not more than 60 volts on this one, and this will still work. And the collector current, as I told you previously, it was 100 milliampere. I guess this is 100 milliampere. I guess this is coming from a different manufacturer. That's why it is 200 milliampere. But otherwise, I will show you data sheet also. It is 100 milliamperes over there. The power consumption or the total dissipation, as you can see the units in milliwatts, and the temperature in which you can store actually is -65 to 150. And the maximum operating junction temperature is 150. So if your transistor is actually going to be turned on and off and something like this is happening, and you are actually having a huge amount of current flowing through it, it will also get hot. But in normal working conditions, it will not get hot. 150 degrees centigrade is a huge temperature. I myself have burned my hands many times, because sometimes the transistor, the resistor is not there. Maybe the resistor turns zero resistance. So what happens? The transistor tries to get hot, and it will go on towards the temperature of 150 degrees centigrade before burning out. So if accidentally you touch that transistor, your hand will be burned down. So be very careful in designing. That's why if I again go back on the diagram, I have used this resistance, this 33 ohm and this 470 ohm, so that I can limit that current. And if I have limited that current, this means that now I am going to have the current reduced over there, so transistor is not going to get hot. Then if I just go scrolling a little bit more, there are some more data. Some of it is concerned with you at present, some of it is not. One thing which you can see over here, it is don't need to go into thermal data. You will get along with this as the course, the next courses in your third year actually come off. At present, you are only concerned with this, that you are actually having a beta. Now all of you, I don't know how many of you still remember that if you are having a transistor, what it does, it amplifies. Okay? So you are having a base current and you are actually amplifying the base current to some collector current over here, and that amplification is based on some beta. So that beta in electrical engineering, now since you are electrical engineering, is called as HFE or DC current gain. Because this is a DC transistor, it's not AC, it can't control AC, it's only DC. So the value of HFE or gain which you can actually control is something from 60 to 100. So nothing more than that. You can see there are a lot amount of different ranges. Why different ranges? Because if the current changes, certainly the amplification value changes. So over here you can see a value of 60, 80, 100, 60, 30. So based on these values, I have designed this values of resistances over there. So maybe at some point we will talk about this one later on, maybe in some other courses over there. This transistor, particular transistor, as you can see, it can reach a frequency, which means you can turn on and off, on and off, on and off at even 1 megahertz. Now 1 megahertz is a huge value. I'm not going to turn it on and off at 1 megahertz because there is no need. Why? Because 1 megahertz means that effectively you are not even turning it off, because the human eye cannot see anything more than 10 hertz. More than 10 hertz, you can't even see it, or maybe like 20 or 30 hertz, not more than that. A human eye cannot kind of. So there is no need of actually turning on and off the 7 segment more than 20 or 30 hertz. That's why even an incandescent bulb, let me talk about that one. You have always had those bulbs, those CFLs at your homes. Now you are applying from WAPDA. There's a 220 or 230 volt coming at your homes, and you have a 50 hertz supply. But if you see with your naked eye on through the bulb or the energy saver or the CFL, whatever, or LED also, you can't see the flickering. Why? Because your human eye cannot see it. Even whenever you are buying a mobile phone, or maybe you are buying a laptop and you are always going on towards the highest refresh rate, partially you can detect it from 30 hertz to 50 hertz whenever you are having it. But yes, you cannot identify if it is more than that. That's why this live picture which I'm showing you at present, I was most concerned because this is a 30 hertz, 30 frames per second live display. I was concerned that I should get something 60 because 30 to 60 a human eye can still detect it because 30 is the benchmark point. So that's why these transistors are capable. You can make them work at even a larger frequency, but their use then not becomes in some 7-segment display. Their use becomes in something else in the later on stage. We'll talk about that. So this is TO292 packaging, and now let me just show you that TO92 packaging. I have that one in my lab at present. I will just show you this TO92 packaging. I have both one of them. I have the TO92 packaging in the bulk also and the MO pack also. Please see this very carefully. This is very, very important. Okay, I have this one. You can see how many of them I have. I have the 5 of them, and these are in MO pack. The only thing difference in that bulk and MO pack, the legs are actually a little bit spaced more. Now I will just zoom it a little bit so everyone can have a, I don't know how many of you can actually see this actually, yes, now. So I hope everyone can have it. Practically when you will see it, you can see the name written on this one. There is written actually that my camera is fixed and the distance is not changed over there. So this is written 2N3904 marking on this one. You can see, and this is the flat side. How flat side? If I can show you on this side, this is the flat side on which the marking is shown. This is the flat side. You can see it's a semicircle over here, and on this side, the flat side, I have the marking written over there. Now if I go back on my data sheet, let me go back on my data sheet, you can see on TO92 or TO92 MEPAC, if you hold your transistor, as you can see over here in this circuit diagram or the data sheet over there, if I hold it, let me just take out one transistor from over here, and if you hold it just like, now I am holding one transistor over here, let me just hold it. Okay, I'm holding one in my hand at present. I hope everyone can see. This is the flat side on which it's shining, and you can see the name written on it, it's 2N3904. Now I am holding it just like this data sheet over here. Now what this means, when I'm holding it over here, this pin is 1, this pin is 2, this pin is 3. So this means over here, this pin is 1, this pin is 2nd, this pin is 3rd. So I am holding it the flat side towards me or towards your camera actually. So this means if I'm repeating it, this one is pin number 1, pin number 2, pin number 3. So the flat side facing towards you, this is 1, 2 and 3, and if I show you again on the camera, this is pin number 1, pin number 2, pin number 2 is this, and then pin number 3. So what this means, if I go back on my data sheet, the data sheet means what is pin number 1? This is emitter. What is pin number 2? That is base. What is pin number 3? Collector. So EBC. Normally, whenever you want to actually remember any data sheet like this, it's better not to remember the whole name. Just see the initials. So E, B, and C. If I go back over here, what was it? This was pin number 1, pin number 2, the second one, and then pin number 3. So this is E, B, and C. E, B, C. So I'm telling you away, I'm again repeating, this is pin number 1, pin number 2 the second one, pin number 3 the second one. So now when I'm going to use it on this breadboard, so supposedly I am going to use it over here like this. I have placed it over here like this. So what was the flat side? I have the flat side over here. So this means, I'm just going to turn it now so that everyone can actually have a view. So this is my E, this is my B, this is my C. So E, B, C, E, B, C. So if I want to now control my common anode point, so if I want to control it through a resistance over here, through a transistor over there, it's very easy for me. What I will do, now you can see there is 7 written, the common anode point, you can see this is going towards the ground. So what I have to do, since this is an Npn transistor, and if I can show you on the, let me just show you a little on the circuit diagram. If I go back on the circuit diagram, I want to control this one. I want to have it. I want to have a 33 ohm resistance from the common point towards the collector. Emitter has to be grounded, and on the base I need to have a 1 kilo ohm resistance. So what I will do, let me just fetch a 33 ohms resistance. I have actually, in fact, 33 ohms is not available with me, but I am using 10 ohms now. Let me just use the 10 ohms now. And I am going to use some jumper wires over here. Okay, so what I am going to do, please see this very carefully, this is very important, because when you are going to design a PCB, how the pins are actually going to be changed. So what I am doing, I have taken this out, this is the common, so that's why now the 7 segment is not working. So I am just going to put it here somewhere. So this is that common cathode point, and now from that common cathode point, I'm just going to take it a very even approach. So this is my resistor. I have used a 10 ohm, you can use a 33 ohm yourself. And then from the emitter, what was emitter? This one was E, second pin was B, the third pin was C. I have connected the collector on this pin, and now I am going to connect the emitter, that is the first pin, and I am going to take it towards the ground pin. In fact, it's not peeled off. Let me just peel it off over here. So this is now going to be peeled off, and I'm going to connect it over here. I'm just placing the transistor over here. Now I want a 1 kilo ohm resistance, and that 1 kilo ohm resistance is going to provide me the base current, so that now I'm going to turn it on. So what I'm going to do now, since I'm not using a dip switch, you can use it yourself. Now see this over here, I have connected. Now as soon as I'm touching the other end of the resistance, you can see the 7 segment turns on. Why this is happening? Now this is maybe a little trick for you, but what is happening, my body is actually providing a little static charge. So that static charge is actually being transferred to the base, so that's why you can see it's little lighted up. It's not that illuminated. So I can even light it up through my own hand. So I'm just providing that milliamperes current, but I want to provide it through a 5 volt signal particularly for this purpose. So what I will do, I will take a jumper wire and I will connect. So this is my jumper wire connected over here. Even if I now connect the other end, you can see now it is turning on. Let me just straight it on. And here, if I will connect it to the 5 volt signal, now this is turned on. So what is happening? As you can see over here, the transistor is working. The same thing, the transistor 2N3904 is now working and it is providing through it. Now I want to turn off, I will turn off that one. I will take it off from that. The transistor is not being provided any voltage. Now yes, certainly if you give a static volt over there, you can see it turns on. So you can use a transistor and you can turn on your circuitry on and off digitally from any controller. So I hope you can use this one. For those who still can't get it, please have an understanding. When you are holding the transistor, the flat side towards you, on the left side, this is pin number 1, then pin number 2, then pin number 3, and then when you hold it over there, this is E, B, C. E, the one, this is the first pin, second pin is base, third one is collector. You can see, I just made it haphazardly, so that's why it's actually hanging. Otherwise, you can see the remaining circuit, which I have done it previously, was like this. So now, what is your work for this week? Coming on to that part. This is the whole circuit diagram. What you have to do, you have to make a PCB in which all of these are going to be added. Now I have already made a simple PCB and I'm going to show that video here in front of you. In fact, let me just, meanwhile, anyone has any questions, please write down in the conversation window, and let me just get that video. Actually, it is, actually I made that video before, so that it's not, does not create a problem for me afterwards. Gee, any questions from the audience? Please ask me. I will actually just play the video. It has no voice or something like that. I just did it before you, before this class, so that I hope this time today I have tried my level best, so that everything that we have done just today, I have tried to explain it online. The camera was set up, I have tried to, and this time today, I guess one thing I learned from the last lecture, actually I'm using two computers at present, and those two computers are actually feeding in the data towards over here, on which I have my LTM working. The other ones I have the circuit diagrams and all that stuff is working, and you can see still my PC is telling me that there is no much disk space left. So still I don't know what problem, but I don't want to disrupt it. And any questions, please, any questions from the, yes, one thing very important, I have gone through some of the assignments, and many of the students were having a problem with the fill area or whatever. I guess fill area, I have answered it very carefully also, that fill area is used for those purposes where you are actually having more current flowing. So what this means actually, that when you are going to have the, okay, I have this actually, the, okay, let me just go on. This is that actually the file. The last time experiment was this one. Okay, I will just give you, I guess there is some question, if Bilal is not answering, I will. Now you can see over here, I have done this fill area. I hope everyone can see this one. This fill area is actually having a lot amount of current. Why? Because this was a common anode. The current was actually traveling through this block connector, through this common anode point, and it was going inside the dip switch, and this was giving the current to over here, and then it was going to, so at this point it was a very high current. So even if sorry, it was 7 or 8 milliamperes of current, so 7 segments, this was something 50 or 60 milliamperes of current. So this means that you have to use a fill area. Yes, certainly one thing more, you will have to use a fill area on this region also. Why? Because it's a huge current on this part as well. So that's why you can use a fill area. But yes, certainly you can't use a fill area in such way that it is touching the other lines over there. I guess there is some questions also. Okay, how to connect resistance with resistors? But I can't get your question. Connect resistance with resistors, what is that meaning? Okay, what are the other two single male headers? Yes, if I go back on the circuit diagram, I told you there are two transistors over here. One transistor is controlling the whole segment, which is actually the common pin, and the other transistor is controlling the DP. Now, from this transistors, apart from that 1 kilo ohm resistance, you are going to connect a male header. That male header, one pin here, two pin header, just like over here on this camera. You can see what I have done. I have taken this jumper wire. Now here you will place a male header. That male header is actually, or a dip switch, that is actually going to control it. So this male headers are actually the connections to your microcontrollers over here. So these male headers, this one. Now please don't confuse this. Actually I can't find a single pin male header. So this is either a single pin here and a single pin here. You can combine these two as one male header, one pin for the DP, one pin for the common. So, but yes, a dip switch is added, so that a dip switch, if you want to control it, because you are just first year students, when you are going to make a PCB, you are not going to have any practical knowledge from the, so when you want to actually make this PCB run, so this dip switches will actually come into play. But when you want to run this PCB through some microcontroller, then these male headers, this pin and this pin over here, they are going to actually be helpful. So these dip switches, when they will be in the off state, you can give the signal from this D0, D1, D2, D3, whatever you want to display, and then one pin data over here, one pin data over here, so that you can control the common cathode pin or the DP point, that is actually the data point pin. Meanwhile, I will just now, I guess, play the so I have this actually. Okay, so I guess I'm just doing this one over here. I hope everyone can have a look on this one. I will share this video as well on the page. You can see how I am placing the equipment over here, and on the data sheet. The same, I am not going to do the whole PCB design, but I am telling you that how you are actually going to find out the different footprints and how you are going to actually use the block connectors and all that stuff. So just go through this recording which is being shown here in front of you. So you can see I am just adding a transistor TO92 packaging. Sir Bilal will share that packaging with you also. I will upload it on my website also. So another transistor, two transistor, you can see the same semicircle. It's not actually a full semicircle, but the flat side on which the marking is there. So please kindly go through this. This is just a simple 20-25 minutes recording. I just did it before so that you can see now what I am doing. I am adding all those equipments which are required first on this one. You can see now I am selecting a resistance from the library, and in fact actually I selected the wrong dip switch. I actually only require a 4 bit dip switch because now the data is only digital. You can see now the F data, and then now I am attaching all the resistances over there, and then let's turn off this power supply. I hope these are just almost the very same things we have done so you can see I actually did this recording so that so proper naming is also a very thing attribute in LTM design, whatever you are doing, and please follow the steps. Certainly always have a naming. I have not gone through your assignments yet, all of them. I have just taken a look at 3 or 4 of them. Hopefully we will give you the result by 2-3 days, but just for now actually yes, there is one resistance extra over there. Anyway, you can have that resistance deleted afterwards. So now one thing very important, as you can see all this is being developed at present. I am using a dip switch. Okay, now here I actually will get the idea that dip switch is wrong, so I will just delete it out, and now I am going to use the again I will go to the dual inline packaging D over there. So how you place the equipments, that actually depends upon how you actually perceive the PCB. So in the first experiment I gave you the whole perceivedness, and for single layer again this assignment today is a single layer again, and this time the size is a matter. This is very important, that try to have minimum size so that your size can actually be controlled over here. Now you can see I have used a 4-bit dip switch over here, and actually that is one, and you're now using these resistances for the transistors over there, and then I'm going to attach. You can see now how the placement, these two resistances which I have just placed just now, just beside the transistors, they are close to the base pin. So you can see they are actually the base resistors. So on the data, on the data sheet actually, or the circuit diagram which I have given you on the website also, and all that, that is the you can see now I am placing them. Now this practice how and where. Now why I have placed them in the bottom, the reason of placing them in the bottom is this, so that because the DP point and the common point, they are also in the bottom, so it's better to I can place them. Now how that whole PCB is going to be crowded, you will actually learn this with some practice, that over here. So you can see now I have named one transistor as digit. So please turn off your mics, beta. Beta, please turn off your mics. I don't need your house codes to be heard over here. So now you can see these are the collector resistances, and I'm now going to, or the emitter resistances over here. You can call them emitter resistance. So yeah, you can see I have called them E resistance, emitter resistance. Here I am also going to call it E resistance, but in fact it is actually going to be a collector resistance. But anyway, whatever happens, so you can see this is going to be that 2-bit dip switch, 4-pin 2-bit dip switch, and you can see now this is going to be actually providing, this is that block connector, which is now, this time I am only using one block connector. One block connector means that it's going to have one pin for VCC, other pin is for the ground. One thing very important, as you can see now what I am using, this is the TO220 packaging for 7805 over here. So I have copied this, and I am going to show you from place components. This is one more library. I will share this one with the Sir Bilal, and he can share it on your website or over there. In fact, Bilal, please turn off your mics. Roll number Bilal 121. Please write down it's absent for today. Please, roll number 121. Samir Arif and 121. Both mark them absent. Bilal, please mark them. Samir Arif and roll number 121. Please mark them absent for today. They will be marked absent for today. Anyway, sorry for others. I'm just making this video again. So I'm now installing that. So I'm attaching that vertical single row flange mount with tab. I will show you this, share this the library. So you can see now it's actually a transistor TO220 packaging. So I'm just going to call it 7805 regulator, and you can just see now. now I am going towards the capacitor. Please go with the capacitor nomenclature which I am selecting over here. You can see what I am doing. I am going with the 10 cross 30. In fact, actually, I am going with the 10 cross 30 or 10 cross 5, actually, not 30. And you can see the size. It's actually a capacitor. I will just show you as well physically also. After this video is over, I will show you that capacitor physically also. You can see the capacitor is having a plus sign, which means that's actually the positive electrode, and then the ground, which is actually the ground pin. So now you can see now I am trying to arrange all this over here, and then I guess one more thing is left. I guess there is the LED, the resistance, which I am going to add over there. One thing very important, miscellaneous connector is the library, miscellaneous connector PCB, from where you are actually going to get the male headers. Male header, you can see this is the 2-pin male header which I am selecting at present, and since a 2-pin male header is required at this point, and then I don't actually, this is the 2-pin male header over here. So this is the input DP and the digit over here. So this is that input DP and a digit, 2 bits, and in fact I need to get it on the other side of the dip switch over here. I will just arrange them a little bit afterwards. In fact, I will hide the overall that structure, because too much of the yellow color on the PCB actually creates a difficulty for understanding the whole PCB. So normally, yes, after some time when you are going to be an expert in all this, here I require a 4-bit switch, so I am going to place that 4-bit switch over this side. Please remember the male header switch is selected on the other side. Dip switch is added so that it can give a 5-volt signal if the male header is not providing anything. So male header is just coming in parallel over there. Okay. Now over here, few more things. I guess one thing you can see, I am saving my document again and again so that it does not, in fact, my document got lost also during all this. And so what I am now doing, you can see I am selecting is pad, and here you can see I have not changed actually the dimensions of my file, so I am changing the units to metric. And now I am doing it 2 mm here, and please use 2 mm as the standard size, at least up till the point when you are going to have all those practices done. Then afterwards, maybe when you will actually physically do PCB design yourself and then solder it, this is also a way how you can actually select from the view workspace panel PCB panels, and then you can select. So this is the hole over there, and now I am going to actually go on with the LED. This is the LED over here. I am selecting it from miscellaneous devices PCB. This is that LED. As you can see, the shape of it is actually telling me that this is an LED, and I will require a resistance over here to actually control the LED is going to come a little bit far, and then the resistance is going to be used over here. So the capacitor is there. All of this work is done. So this all management, I will show you some of the nets also in this video, but leave the PCB design to you. The most important thing is the PCB design, which you have to do. Again, one thing very important, last time I guess there was some miscommunication on this one. The assignment deadline is always Sunday night 12 AM. Every time the assignment deadline is Sunday 12 AM at night. Sunday, the night of Sunday, that is the deadline for the assignment. And certainly, yes, as this will go on a little extensively, or maybe we have a little big design, then certainly we can give you more date. But for at least for this assignment and this week and the next one, this is going to be on Sunday. Actually, I wanted it to be on Sunday, but last time also, but your CRs actually asked it for 1-day extension, and that's why I could not go on through the assignments which we have submitted. And please adhere to the time restrictions for this one. If Sir Bilal and I have told you that it should be 12, it should be 12. Anything apart from that certainly means that you are going to go towards reduction. So this is very important. You can see now I am appointing the nets on the PCB diagram, and I am using the nets over there for all this one. So you can see the TO220 packaging. So actually this is the new thing for you, and I have shown you the transistor also physically as well today, and I have shown you how you are actually going to hold it. The pin, the footprint of the transistor also has the logic over there, the 1, 2, 3 pins. So I'm just going to add some more pins. This is the LED, and then you can see this is the LED from where the LED resistor is actually going to be turned on. This is going to be 330 ohms or 470 ohms. The LED is going to be something red color or the green color or something like that. And so this way, I guess this is the 7 segment over here, the common cathode, and in this way you can have that common cathode point, and that can be connected to your resistor or whatever 5 volt. This is the 5 volt pin, and here I'm showing you the dip also, the 74HC4511. Now you can see I'm pointing D0, D1. In fact, I have missed some nets actually, so I'm going to make those nets as D0. Please either use small letters or either use capital letters. All, don't make it a mix of both, because otherwise it becomes difficult for. But if you can handle it, it's as such no limitations. So you can see now I am appointing D0, D1, D2 and D3. Certainly, actually I remember the data sheet, so that's why I am not opening that data sheet every time. But since you are just going to be newbies, so you are not going to have anything over here. Don't forget to select pin number 3 and pin number 4 as 5 volt and pin number 5 as ground. That is a must over there. And this is going to be D3. So you can see now it is connected. Now I could have used it in the same direction just like the IC, but I want the dip switch to actually behave as D0 and D1 and D2, D3. Certainly D0 is the one, and now I'm having D1 and D2 and D3. So it will be better actually, because when you are controlling it physically, so you know the least significant bit is the farthest most point on the left side, or the right side actually, sorry. So you can see this is a dip switch, and all these 4 pins on the other side, this one which I am double clicking it, it's going to be connected to 5 volt. One thing very important, this whole PCB has a VCC which is the input voltage, and 5 volt which is the regulator output voltage by which all of this PCB is working. One thing very important, there when you are going to auto route this PCB afterwards, when all the connections are done, you are again going to do it single layer, but when you are going to route it, they are going to be contentions, so be ready for contentions which you have to actually remove yourself. Okay, so this is all. I guess I could not go beyond this point. This was all the resistance or whatever over here. So this is the 1 kilo ohm resistance which we have to add, which I have added also on the dip switch. So just see this 1 kilo ohm resistance, how I am adding this one over here. This is a very important resistance. If you don't add this resistance, you are not providing zero ground path to the A, B, C, D or D0, D1, D2 and D3 pins over there. So you will see what I have done. I have placed them in such a way so that D0, D1, D2, D3, the one pin is going to be connected to D0, the other pin is going to be connected to ground. So this will actually come on when you are actually going to be connecting them, maybe a lot of PCBs you are going to make on. This is just your second assignment at present, so maybe after the 4th or the 5th, maybe we are going to go towards a lot of complex designs in this software. Maybe like this time I expect to go on towards 4-layer PCBs or 3-layer PCBs also. So hopefully we will do that, and maybe if we go on campus certainly and we decide on something for the projects also, then maybe I can select 3 or 4 different projects which we will get them manufactured from China for at least 4 or 6 layers of PCBs. So I guess only this portion is enough, I guess, and I hope so. The remaining nets and all those transistors configuration, you can do it yourself, and this one can be done very easily, as you have seen. I will share this recording also with you if anyone is interested in that one. Meanwhile, this is the circuit diagram which we want you to actually use for this PCB design, and this is single digit common cathode 7 segment driven by 74HC4511 and a dip switch. I have used 2 block connectors over there. Even if you use one, no issues on that one, because the PCB design which I have used over here, this is using this is the same dip, the same file which was just showing you the PCB nets and all that stuff. I have not done all the nets and wiring, and I have not done the outer routing. I am leaving it to you because you have done that. Just 2-3 things very importantly. 2 tracks, they should not be very close to each other, just like this one. If this track was like very close to like this one, so if this one was very close, so just let me select actually. So okay, this is not moving. So if this one was selected, so if this one becomes very close, you can see there is still some clearance, but when you are going to physically make this PCB, it's going to be very difficult to actually make that PCB. So over here, this has to have some difference in between them. I'm not giving a value at present because you're just newbies at present. I'm not going to make you over here. You can see the difference in these 2 tracks is a little bit more. Plus you can see the tracks limits over here. Meanwhile, when I will go through all of your assignments that you have submitted, hopefully in next week I will discuss some problems which maybe some problems which are common in all of you. I will discuss those problems. Meanwhile, if anyone has any questions, please ask me in the conversation window regarding this experiment or the experiment which we have done previously or something like that. Anything, please ask me. Well, let me just close these windows. Actually, maybe my memory is on a low side at present. So this is that circuit diagram. Any questions, please ask me just now.